Okay, so we are now recording. So let me share the screen. Okay, so basically, I'm in the folder and we're going to test out that DuckDuckGo. I'm going to create a new 3. Okay. So they recommend, so it's in the, you guys should be seeing this application. Let's try that. All right, I'm going to create a new one. All right, so from Fastbook, import all URL search images. Owl. Max images 100. Oh, that's a lot of images. Len URL. So let's run this. Missing graph viz. Uninstall Fastbook.
I get that warning, but running the conda install fastbook doesn't fix it. But I don't think it does anything.
Yeah, it's just a warning. I actually installed Fastbook before, so it's strange. All right, I was able to get, it seems like I got something here, right? Because these are the URLs of images. Length URL says 100. And then if I print URLs, just the whole URLs.
You made a typo.
Yes. Okay. So yeah. So there are the links for the owls. So now, according to this, the URLs are returned as strings, so you don't need to use attribute got. Now we just do download URL and open it. So yeah, and then you tell it where you want it and the name of it, basically. So let's try that one. Oops. Okay, so now URL 0, that's snowy owl, beautiful snowy owl. And it's gonna save it into images. Let's, I guess, owl 1. You'll have, you can maybe think of some logic for this. Owl 1. And then I'm gonna show it. Okay. That's a thumbnail. So let's see what happens. Okay. Yep, there it is. It downloaded all the URLs and it created the thumbnail. And then if I look in here, oh, there's images now. Can you guys see that? So images is here, and if I click on that, there's only one out. So how do you download all of them? Or did I just download one?
You just downloaded one.
Yeah, okay. Download URL 0. Yeah. All right, good. Okay. All right, good. So you can see Jeremy is saying that if you still want to use Bing, you can just replace the image search Bing function with image search DDG. So you can also try that. But this should do it as far as downloading the images. If we try another one, 7. And there's another owl. Do you guys see that? Jason, does this kind of address your question?
I believe so, yeah.
Yeah. All right, so you should be able to do it with this, hopefully. Try it out. You know, again, I'll give you guys an extra week for it, so I'll extend the deadline for it. But great. So two options now. We have both both Bing API or DuckDuckGo API. I'm going to change the name of this, and I'll load this file later. This will be DuckDuckGo image. Let's call it API. All right, so hopefully that takes care of that. All right, and then now we should be ready to begin with today's discussion. Any questions before I begin? All right, doesn't sound like it. So today, actually, what we're gonna do is we're gonna get into the fundamentals of machine learning. Now, in the first 4 weeks, we've looked at the power of fastai, right? And everything that we can do. We've looked at transfer learning and how that works. Today, we're going to get into just some of the basics of machine learning from the point of view of image processing of computer vision. So we'll go through that. This should correspond to, I think, chapter 4 of your book. And then it's a pretty good introduction to PyTorch and to various other things. So it should be pretty interesting. All right, and we'll go over just a basic background of deep learning, okay, which will help us out as we move on. So as I said, fastai is very much focused on image processing quite a bit, and so we'll cover that. We're doing the transformers module from Hugging Face to cover natural language processing. I'll leave a few minutes at the end of class today for us to discuss, because you do have that mini project, so we'll see where you guys are on that one as well, and we can have a discussion, okay? All right, so if there are no questions, I'm gonna go ahead and start up a new Jupyter. So you should be seeing a new Jupyter, and we're just gonna go through the lecture for today. This code is already posted on the GitHub under computer vision. You can just take a look at it if you just want to read through it. All right, so let's start with, our analysis will begin with, or we'll focus on just MNIST, the classic data set for image processing, developed by Jean LeCun and his team. So we're going to just use MNIST. But actually, we're gonna do some interesting things, and I'm gonna discuss something that it's not gonna be homework, but it's something just fun that you guys can do if you want to. And so I think it should be pretty neat. All right, so let's go ahead and import the library. So from fastai .vision.all, import all. And let's also import NumPy. Now this won't be the full MNIST, we're just gonna use classes 3 and 7. So it's just gonna be, let's say not full MNIST, just classes 7 and 3. So I've covered some of these ideas in previous courses, either in the 365 or the 520, but this is an interesting perspective. So it should be pretty useful. It's also focused on PyTorch. And so we'll go actually very, very deep into deep learning with these ideas. So let's use the path first. So I'm going to do path on tar data. And then we're going to do URLs dot MNIST MNIST sample.
We can't see what you're typing.
I can see it.
Yeah,
Yeah,
I
I
can
see it
see it
too.
as well.
Can you guys see it now?
Yep.
Jeremy,
Weird,
can-
mine is stuck back on. I just see a static image of your Jupyter notebook folder. Let me
I've
leave and come
seen
back.
what you're doing. Yeah.
I'm at path. I've typed all of that.
I think the rest of us can see what you've been doing the whole time.
Okay.
It looks like he just restarted.
Yeah, can he just, he can get out and then I can get, yeah, exactly. And then I can admit him back in. Okay. Jeremy, can you see it now?
It's working now.
And this should be recording also. Yeah. So it's recording as well. So we're going to be playing today with computer vision. We're going to be playing with images. And then along the way, we're going to look at the fundamentals of machine learning and deep learning. And so it should be pretty good.
Professor,
Yes, sir.
you spelled URLs incorrectly.
Oh, did I? Okay.
Yeah.
Yeah. Thank you. Yeah, thank you. And so, because a lot of the things are computer vision later on, this will be very helpful. So we've got the path. We untar the MNIST sample data. And then now let's take a look at what we have in here. So let's do print path dot list. So I'm going to actually rename this. I'm going to call it fundamentals ML with MNIST. Okay. Save it. And now we can run it. Okay, and it ran correctly. And you can see there we have downloaded MNIST sample. We've got train, we got the validation set, and then we got label CSV. So we've got the data that we need. Now we can proceed. If we just want to see what's in train, for instance, we can do print. Print do here I'm gonna do path / train. And then, so we're just going to look at the train set, and then I'm going to do ls. Okay, if we run this one, there we can see that in the train set for this sample MNIST, we only have 7 and 3. So if you guys remember, the MNIST data set is the data set that was developed for recognizing handwritten digits. So basically, this system was actually, the goal was for the mail, right? They would look at the letters, we all write zip codes. And so they wanted to sort the letters by zip code, but people have written by hand. And so they just wanted a system that can recognize the zip codes, handwritten digits, and then kind of sort the mail. John LeCun, who is currently the director or VP or something like that, he's the head of AI at Facebook or Meta, no? And he is he developed this. He was one of the pioneers. This was a long time ago, by the way, when deep neural networks were not popular, but yet the system actually worked. So he created it with his team. Okay, so we listed that we have 3s and 7s. Now we can create a list basically of this data. So let's create 3s. Okay. And so let's call path from the train set train. And then we've got the 3s. We're going to list them. And then we're going to, sort it. Okay, we can repeat the same process for the 7s. Create the list of the 7s. Path. Train. And then this is going to be 7.ls. Sorted. We've got both sets now, 3s and 7s. Let's see what happens. Let's just try to print something. So I always just like to view things. Let's see, 3s. Run it. All right, and you can see there, it's got basically the list of all the images, the path, the full path in the file system. So there's a lot of images there, as you can see. So let's comment it out. And now let's view one of the numbers, so one of the handwritten digits. So we're going to go ahead and grab image 3_path. Okay, and from 3s, we're just going to grab one of these. So 3s, grab, index 1, let's say. Remember that PyTorch and fastai use pill. This is pill. And then now im3 image dot open, and we're going to open basically im3 path. Okay, so let's go ahead and save it and run it. We need to, okay, so it's in the format. Now we just need to show it. So here in Jupyter Notebook, it's pretty easy. im3, and there it is. There is your handwritten digit from the MNIST data set. Right, remember this is a 28 by 28. These are the famous 28 by 28 images. And this is grayscale, so it's values from 0 to 255 in grayscale. Okay, so pretty easy, pretty straightforward. If you have any questions at any time, stop me. Okay, so now let's think about looking at the image as a NumPy array and PyTorch tensor. So remember that NumPy arrays and PyTorch tensors are not the same thing. In terms of the data structure. So they're independent data structures, but they're pretty much, they mimic each other. So everybody has always tried to be like NumPy. So they always, and in the past, it used to be that things were very incompatible. Now with Torch or PyTorch, NumPy and PyTorch tensors are more compatible. FastAI has tried to take that even further. So it's pretty good. But let's look at the image as a NumPy array, right? As a NumPy array and as a PyTorch tensor. Remember that a tensor is just a generic name for multi-dimensional arrays, including vectors, and NumPy arrays are kind of the same thing. So if we want to view the data, we can just slice it from the image. So we can do print, make it a NumPy array, NP array, and then the original image that we want will be IM3, right, which is this one. And then now this converts it into a NumPy array. So now we can just go ahead, since this is an object, right? That's a NumPy array. Now we can just slice it. So in this case, just so that we don't have to show the board, the background, for instance, so just we're going to focus on kind of the center. So we're going to do from 4 to 10, and then from, let's say, 4 to 10. Okay, so if we print this one, save and run it. You can see I basically got the data now. Background is 0, right? And then here we have the pixel values for all the individual pixels, basically. Hey, we can do the same thing, just use a tensor instead. So I'm just going to copy this one, Control V, and now this is going to be, notice how you can just write the word tensor in FastAI, because we imported FastAI. I didn't have to declare PyTorch or anything like that. So I just type tensor, IM3, and then slice it again, run it, and you can see the difference is it tells you the torch data type. It's a different structure, but you can see the data is there, basically. Okay, so we can view the tensor and make sense of it. So now let's so now we're going to take the image, slice it again, put it in a data frame. And we're just going to change the properties of the image so that we can view it a little bit better. Okay, let's go ahead and do that. And we should actually see a shape for it. So let's try import pandas as PD. IM3 as a tensor. We take the tensor from IM3. Okay, then we're going to create a data frame in pandas so that we can manipulate it further. So PD data frame. And this is going to be IM3, that IM3T. Let's slice this one since it's already a tensor. We can do from 4 to 15. And this one's a little bit bigger, from 4 to 22. Okay, so once we slice it, we're going to increase the font size of this a little bit, make it a little bit bigger, and put a background gradient of gray so that it shows a little bit of grayness in the background. So let's do that. So data frame style, set properties. Okay. And we're going to specify a font size. So I'm going to do single quote here. Font size. Six point. And also the background. Gradient. This is just for presentation to view it really. And then here we're going to say grays. Okay, so that should do it to give us a nice view of it. And you can see that there. You can see that the effect is that it captures the intensity, right, of the grayscale values. So darker, the closer to 255, the darker it is. And then if it's like 126, you can see it's like a less dark gray, and then 74 is even lighter. And then 10, 8, and 0 are very close to white. So you can see there, you can almost see the shape of it. It looks like a 3, basically, the top of a 3. And so that kind of represents how the data is stored on the array that represents the number. Any questions so far, guys? No? All right, so now what we want to do is we want to save the data, but this time we want to save all of it because now we're going to process it with machine learning. So we've got to grab all of these grids from the data set and store them as basically some type of a tensor, right? So we're going to do that. So I'm going to call this, we're going to, since we have 2, we have 3s and 7s. I'm going to say 7 tensors. And I'm also going to create 3 tensors. Okay. So we're going to go with that. Okay, so we're going to create lists here. We're actually just going to do a list comprehension. So for O in 7s, right? So if you remember, 7s just contain, we printed it somewhere here. 7s just contains the list of the files, right? So, you know, the list of the files, but now we're going to get that file path and read the actual image. So for O and 7s, now we're going to call image dot open, and then we're going to do O, the letter O, and then this reads it as an image, pill image, so we need to convert it into a tensor, and so I'm just going to call the tensor. So this will make them into PyTorch tensors, basically. I'm going to repeat the same thing for O in 3s. Okay, for O and 3s, we're going to read the image again, image dot open O, and then this is also converted into tensors. This now will give us the list of our tensors, basically. Just like that. So we have, okay. And now we have the data read in so that we can process it further. So if we take a look at the size of it, we can do print of all the tensors. So we can do length length of 7 tensors. And we can also do print length of 3 tensors. Okay, so I'm going to save and run that. There you go. So we've got about 6,265 in one and about 6,131 in the other one. Does this make sense? Guys?
Yep.
Yep. All right. So now let's print out one of the images in this 3 tensors, right? So I'm going to do show image. Show image. 3 tensors. And let's just pick one, you know, at random, because it's a 3, obviously it's going to be a 3. Let's pick 4. Let's run it, and you can see it looks like a 3, right? You can try different ones, different indices there, just so that you can see that they vary slightly. So if I do another one, but it'll be a different index 7. And you can see these two actually look really different as far as 3s are concerned. All right, so we have so this is the idea, right? So we have about 6,000 versions of a 3, 6,000 versions of 7s. And then we want to try to train a model to figure this out, right? So to do some prediction. Now, the thing that we're going to need, because we're talking about tensors, is that we want to create the whole data set as just basically an array, right? In this case, it's going to be an array of 28 by 28 by 6,265 for one. And then the other tensor would be 28 by 28 by 6,131. Okay, so we're going to create, you know, we're going to stack them basically and create these really long cubes that will contain all the images, if you want to imagine it that way. Okay, so let's do that. This is the beauty of you know, of deep learning, right? That we can stack our data like this. And this is, you know, one of the key insights. So let's say make all images in each list into one cube, a long cube, which, you know, the formal term should be a tensor of dimension 3. Sorry, 3. Okay, 28 by 28 by 6,265. And it's going to be also type float and normalized. So normalized just means, if you remember, the values go from 0 to 255. But if we divide them by 255, then 0 divided by 255 is 0, 255 divided by 255 is 1, and then anything in between, right? So it's going to basically normalize them to between 0 and 1. So let's do that now. We're going to create a new list. Let's call it stack 7s. And so we call torch.stack. And we're going to take the original list that we had of tensors. You can see that here, right? We read the images and then we converted them into tensors. So now we're just going to grab that object, these objects here, and we're going to stack them into one single tensor for processing. So let's take a look at, so torch stack 7 tensors. And then we're gonna, once we've created that, we're just gonna make them into float. Set the data type to float, and then also by doing this, we actually can normalize every single one, all the pixel values in these tensors, right? Dividing them by 255. We're gonna do the same for the other ones. I can just copy this. So this is going to be stack 3s. Once again, we call torch.stack. This is going to be 3 tensors. Dot float, and then normalize to 255. So basically, we have one single tensor now, a very long one, and the data is normalized. So now let's print out the shape. You know, printing out the shapes, remember, is always very useful. So in this case, stack underscore, let's do 3s. And then we're just going to call shape, and we're going to print that one out. Okay, and as you can see, it is now a single torch tensor of size 6,131 by 28 by 28. So basically it holds all images as these slices, these 28 by 28 slices in this very long cube. Make sense? So notice how that's the power of tensors, and that's when you know, a lot of the libraries in PyTorch are designed to process data exactly like this, efficiently, by doing matrix multiplications. Let's take a look at the tensor rank. The rank just means like the dimension, so there should be 3. So we're gonna do tensor rank, which is basically the dimensionality of the vector space. Okay. So all we have to do is we can print out stacked 3s dot n dimension. Okay, so now if we save this and run it, you can see it's got a rank, what is called a rank, which basically means the dimensionality of it, which is 3. So this should be pretty easy, right? That's just very basic stuff. Now what we're going to do is actually we're going to do something really interesting. And this is where I was saying this is something that you guys actually could do, you know, in a different, you know, in a scenario that's unique to yourself. So let's think about what I'm going to do here. So I'm going to take, remember, I have, let me actually go to, I have basically a cube, right? I have a stacked cube, and it's got 6,000 images. All are 28 by 28. So what I could do actually is that I could take the average of all of those and create a new image that is 28 by 28. But that image is basically the mean of it. So actually, I forgot to install my tablet. Give me a second. So I have it All right, so I'm going to switch over to the whiteboard here. Okay, so you should be seeing the whiteboard. So if you think about it, what we did is we had these images, right? So we have image of a 3, and then there's another image of a 3, and then there's another image of a 3, and then there's another image of a 3, right? So we have, and then dot, 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 because we have about 6,100 or so of these. So then if you imagine, we can just like stack them all, and they're like cards, right? So they're all pretty close to each other. So basically it created this really long cube, right, of all 28 by 28 by 6,100 or so. Now what we want to do is we're going to average all of these images, right? So we can calculate for every pixel, you know, we know that there's 6,100, so we can basically sum them, divide them by the number, and then we can arrive at an average. So what this gives us is that when we create an average image of this stack, it's going to be a combination of all of these, right? So it's going to be like a new image that has some of the properties of all the images. So it might look, you know, it takes a little bit of everything, right? So it kind of comes out different because it's the mean overall. So this is actually a very common thing that's done in machine learning, and it's a very powerful thing actually that we can do. Okay, so let's go ahead and go back to the Jupyter notebook and calculate the means basically. So calculate the mean. Calculate the mean of all images in the tensor, in the stacked tensor. Okay. And what this basically means is for every pixel position, this will compute the average of that pixel. So we should say that. So for every pixel position, this will compute the average of that pixel. Okay, let's just say over all the images. So to do that, it's basically we take mean of the 3s, right? So to do that, all we have to do is we grab stacked, because we already have it as a tensor. So we grab stacked 3s. And then we're just going to invoke the mean. Okay. Now we want to specify. Oh, there's two. Yeah. We also need to specify one more thing, and that is the dimension along which we are going to do this. So do the average. So what that means is if we go back to the whiteboard, you know, a lot of the time in deep learning, these are the tricky things, right? So this has 3 dimensions, right? So if I use a different color, let's say green, there's that dimension, there's that dimension, and then there's that dimension, right? So that's the first dimension 0, and then the other ones are 1 and 2, right? So we are going to do the average along this dimension in that direction, right? So that's the 0 dimension because it's every image, right? For every pixel in every image. So we're going to take, you could have taken averages in other ways, but this is what we need for the mean for all images. Does that make sense? Okay, so then we specify here the number 0 for the mean. So we can just say here to simplify, 0 refers to the 0. Okay, and then now we've calculated the mean. Let's do it also for 7. For the 7, so I'm going to do mean 7 stacked 7s dot mean, like that. Same thing, the axis. All right, and now we have just one image that is the average of all 3s and one image that is the average of all 7s. So let's try to visualize it and see what it looks like. So we can do show image mean 3. Show image mean 7. Okay, we can add semicolons here. Doesn't show any other stuff. So now let's save it. And if you believe it or not, that 3 and that 7 are the averages of all those images. So of the 66,000 or so, 61,000, 6,131, right, of the 3s, that's the average 3. That's what an average 3 looks like. What do you guys think? Isn't that interesting?
Yeah,
Now
it's
it's
pretty cool.
pretty cool, right? Yeah. And actually, we're gonna take it first. Let's look at some insights, and then actually we're gonna think of something else that I thought was pretty neat. So the first thing is a key insight. Look at these images, and what you will see is that some areas seem to be maybe like the color is more solid or fixed, whereas other areas the color is more blurry. Do you see that there's like certain areas that are more blurry than others, basically? And the key insight with this actually is that the more fixed or darker, let's say, the image is, the more it matched, that the more agreement there was among all the images. Whereas wherever you have blurriness, that's where the images had more disagreement, so they didn't match. You see, so it kind of makes sense that it's towards like the ends, right? So you notice at the ends, everybody will mark like this curve, but then the ends of their numbers change a little bit more. So that's why it looks a little bit like this blue haze, if you will, that blurriness. It's because people were not consistent here. Everybody had their own way of pushing the line of the number to one side or the other, if you will. So that's kind of the insight. So it is darker where all images match, and is blurry where images do not match, basically. So that's kind of the idea. Now, what's great about this is we have created, if you think about it, an idealized version of 3s. By taking the average, it's kind of like we're saying, well, the average represents what everybody agrees that a 3 should look like in a way. So that creates for you a new 28 by 28 image that is the average, right? The normal. If you guys remember your statistics, right? The whole point of statistics was what? One of the things that we learn in statistics is, a normal distribution, right? So in statistics, you have the mean and the standard deviation, right? So that's central. So you have something like that, and there's your mean, right? And then there's your standard deviation and so on, right? Your variance. And basically, those images, all those 3s or all those 7s, so I'm going to use a different color. So let's say I'm doing 3s, right? So all those 3s fall, okay, that's not a 3. all these threes are there. But out of all these threes, it created that mean three, right? That mean three that's, you know, overall. And then now what you can do is you have a way, because remember that the images are 28 by 28, right? And so you can create basically a vector space, right? For these images. And, you know, this is 28 by 28, which becomes 784. So this is 784. And then now you have a way in that vector space. I'm just going to draw it as 3 lines, but it's bigger, where you can put all the threes, but you have one central 3, one mean 3, right? So now you can calculate, right, the distances between all the images and that mean 3. And so you would, one could make the argument, well, the threes that are closest to the mean are the best threes, and the threes that are furthest away from that mean 3 are the worst, if you want to think of it that way. Does that make sense? So in itself, that can be a type of a machine learning technique, right? Where you want to, if you're building a classifier to detect threes confidently, you could build it like this. You find a mean, and then you compare all the threes to the mean, rank them, and then you'll have means that you'll have threes that you trust and threes that you do not trust. Is that clear?
Yeah.
All right, now I want you to think of this. This is a thought. I thought about doing this a homework, but you know, probably not. You already have plenty of homework. So let's call it a thought experiment. So this might be something that you want to do. So we all have pictures of our family, right? So we all have like pictures of your, your parents, your brothers, sister, cousins, aunts, everything. So I thought it might be interesting to you, just for fun. If you want to do it, you don't have to. Obviously, you have to choose images, a specific type of image. But what you could do for fun, and then show it to your family, is you could pick a whole bunch of images, right, of your family. Obviously, they have to be the same size. Anything above like 300 by 300 will be difficult for machine learning for the software that we currently have. So you're going to have to resize them, which you already know how to do, and also crop them or something, because they need to be the same size. Let's say, for the sake of argument, that they're 28 by 28, although that's pretty small for this kind of exercise. So then what I was thinking is, just for fun for you guys, is you could take pictures, especially if you can find a whole bunch of, there's usually a lot of pictures that are like photo IDs, right? So photo IDs, there's a background, passport IDs, etc. And people just kind of look like that, right? So if you could find a whole bunch of pictures of your family, and of course it matters if it's color or black and white, etc. So, but if you could do that, find a whole bunch of pictures, I don't know, 30 maybe if you can find them, and then do this, right? Stack them. Again, make sure they need to be the same size, 100 by 100, let's say. If they're color images, you may need to just make them grayscale, right? Or you might do the R, the G, and the B. That's another solution. So you could do like, stack R, stack G, start, B. And then you can probably see where I'm going with this, because it might be funny then to calculate the mean of your family. Do you guys see that? Obviously, you wouldn't have 6,000, but you might have 30, let's say, and these are 100 by 100. And if they're like passport pictures or ID pictures, you can take then the mean, and now you will have the mean of what your family looks like. Does that make sense? So, and then another thing that you could do then is, if you take the difference between all those images and the mean, you could, in and this is not a scientific answer by any means, but in a funny way, you could say, which relatives look more like the mean of your family than other relatives. So you can actually do something like that and just have fun with it. So anyway, that's kind of something that I thought would be fun. Anyway, are there any questions so far?
Nope.
All right, great. So now that we know how to do the stack of the numbers, right, and then calculate the means of them, you know, and basically it's a tool for machine learning. It's useful. Now what we can do is, let's see, we got the means. Yeah. Now let's do that. We're gonna try to measure the distance between one image and the mean of the images for similarity, which is the scenario that I was talking about. So let's go back to the Jupyter notebook, reduce that in size a little. All right, so now, now we will measure the distance between one image and the mean of all images for similarity. So this is a very standard thing, very important thing in machine learning. So we're just going to get any image from the stack. So let's call it A3. Okay, and we're going to call stacked threes. And from it, we're just going to grab one image by index. Let's say 1. Okay, got that. Then we're going to do show image A3, just so we can take a look at it. So we're going to slice one out, save it, run it. It's an error. Show image.
Yep. Yes.
All right, there we go. So this is one image. So this, you know, in the scenario, this would be like, let's say, you know, someone and then the average of their family, right? So it's the average of your family. This is you. Obviously, threes look a lot more alike than your family, but it might be interesting. So anyway, once we show the image, now we need to calculate some distance measure. So there's a lot of distance metrics out there, but they're usually pretty straightforward. So let's do, these are called either, the ones we're using are, so we're going to calculate what is called the L1 norm. And they just have fancy names, but they're pretty simple actually. Or calc the L2 norm. And basically the difference is that one squares the data, one uses absolute value. That's really all it is. So we're going to do L2 norm here. So to calculate the distances, we're going to, let's say distance three, and this is for absolute value. So we just take the difference as these two are tensors, right? We can just easily say A3 minus mean 3, right? And that's given that they're tensors, it just takes the difference between all the values. Since some values might be negative, others positive, we're going to get rid of that by doing absolute value, so that we only capture the differences and nothing more. So remove the symbol. And then after that, out of all the values that we have, we take the mean basically. And that gives us a metric for calculating distance. For the other one, we can do the exact same thing. Distance but now square root. So I'm going to do still 3s because we're calculating in 2 distance metrics for each one. Okay, I'm going to do the same. I'm going to do A3, A underscore 3 minus mean 3. And then we're going to do dot absolute, I'm sorry, not absolute value. This is going to be raised to the power of 2. So it's just like that, square it. It'll apply it to all the values in the tensor by doing this. And this one needs to be within parentheses because the result of this operation will need to be, we'll calculate the mean of this. And square root. So this formula, actually, you're familiar with. You've seen it before. Let me switch over to the whiteboard. So that formula is the root mean squared error, or the least squared error function that you use in linear regression, for instance. So it should just be the sum of the squared errors, right? So the sum of the squared errors like that, right? So that's basically the formula that we're doing, which this derives from Pythagoras, right? So triangles. So we know that, what is it? A square equals B square plus C square, which becomes the distance is square root of B square plus C square. When we generalize here, it kind of generalizes like that, okay? But that's the formula that we're doing, and this is called RMSE, root mean squared error. It just calculates the differences between 2 values, because this could be negative or positive or whatever, and they cancel each other out. We square them. That takes care of the symbols, and we just end up with the difference. We sum all of them, and then we can calculate the square root. Okay, so go back. That's what we have here. So we take the value for that image, for that one image, and then we take the mean, and then we square it, mean, and then the square root. Any questions? And so now if we proceed, let's print out the values. What's important here is to use these as to compare, right? To compare the distance. So if I do print let's say a free image to mean 3. Okay, so we're going to measure the distance between that value. So this is how you would measure, like if you did the example I told you about, calculate the mean of your family, and then each image you compare to that mean to see whose relatives are closest to the mean of your family, right? So here we can do print, and we're just going to look at the different values. So distance 3 absolute, and then here print distance 3 square root. So these will be different values, but against each other, they really have no meaning. Okay, so they should have no meaning. It is when you compare them to other distances that, that they should matter. So you can see here the tensor, one is 1 One is 0.11. The other one is 0.20. So these two have, they're not really, you don't compare one to the other. Instead, what you would do now is if you had a 7, right? And then now 7 minus mean 3 of 3, that 7 should be further away than the 3. That's really the trick. Okay, so here we're just printing out the distances. Now let's take, for instance, what I was saying. Let's do. Now let's compare the same 3, but to mean 7. Okay, let's do that. So we're going to compare. So it's going to create distribution distance. 7. And then we can calculate both variables. So absolute and also distance 7 square root. Okay, so we have both here. So now we calculate the distance between A3 minus mean 7. So it's the same A3 that we use up here, but now we compare it to mean 7. So these distances should be, bigger than the distances between A3 and mean 3. Allegedly. So let's try it. So dot absolute value mean. Do the same here. So this is going to be A3 minus mean 7. Square this. Raise it to the power of 2. Then dot mean. Then dot square root. All right, and now we can go ahead and print these values. So these are a 3 image to a mean 7. Okay, so we're taking this to mean 7. So these distances should be greater. Okay, so let's just print it out. Print distance 7 absolute. Print distance 7 square root. Yeah. Okay, so actually I'm going to move these here. And let's add a little line here. All right, so now let's run this. Okay, and as you can see, the distance, so if we just look at the absolute value distance, so we look at this one and we look at this one, right? So those are the two that we compare, the absolute values. 3, the image 3 is closer to its mean 3 because it's 0.11 versus the 3 image compared to the mean 7. So if you look, the distance is now 0.15, so it's greater. So it tells you they're more different because it measures a similarity. The same applies if we just use the square root. So the square root distance, okay, which is the L square root is actually L2 norm, RMSE. So if we look at the square root, is 0.20 between 3 and a mean 3, and it is 0.30 between 3 and a mean 7. So the longer the distance, the more different they are. Does this make sense? Do you agree that it works? Any questions, guys? No questions? All right, so it makes sense, it seems. All right, good. So it is 3:50, right? So we start at 2:30 to 3:30 to 3:50. So it's an hour and 20 minutes. So we'll take a 10-minute break from 3:50 to 4, and then we will come back at 4. Right? That's, guys?
Sounds good.
All right, so we'll take a 10-minute break from 3:50 to 4, and then we'll continue with this at 4, okay? But we've advanced a little bit. All right, so I'll see you guys in 10 minutes, and I'll generate the video. So I'll get out of this soon.